Okay, good. So, good afternoon. I'm Jason Gilmore, representing Airbus Defence and Space. I've put a picture of myself up on the front slide because we're not allowed to use our cameras on our laptop. So that's me. That's me sitting on the famous light rider bike that was done by AP Works in Skelmalloy a number of years ago. So this is going to be an overview of both powder and wire technologies, and talk about why we entered the journey of additive manufacturing back in 2007. So at the time, I've been at Airbus, the former Astrum company, for just under 20 years now. I spent the first 12 years in the antenna group, and we were thinking that antennas of the future would be extremely complex compared to the technology of 15 years ago. And the photograph on the top left is a high performance RF part. It's the heartbeat of an antenna system. And we designed this about 18 years ago, and it was manufactured via spark erosion, and we required 2 of these per satellite. And that small assembly that's about 120 millimeters long is 4 spark eroded parts, and these are effectively handcrafted. It required 96 different shaped electrodes because of the internal geometry, and each one of those assemblies cost about £15,000. And what we thought is, the antennas of the future, we may need 100 of these per satellite. So not only would it be prohibitive from a cost point of view, there's not too many spark erosion companies out there. So we worked, ended up being the first ESA funded project on ALM. I need to be careful with my words. It's the first externally funded ESA project. They did some work in 2005, 2006 on AM internally. But the project really was to look at the alternative manufacturing technique. So for antennas of the future, we were spending not 15,000 per assembly and 16 weeks. We were almost chucking these out production style, albeit production rate of 100 is fairly large for the space industry. So we went around a process of looking lots of different technologies, from electroforming to casting, and we stumbled across an EOS M270 by a company called CRDM in High Wycombe, that were later to become 3D Systems, who are now Quick Parts. And they had a material called DM20. It's no longer there, probably due to the high levels of porosity that we saw. But the point being that we managed to make 9 of these components in just over 24 hours using this unsuitable material at the time, because aluminiums weren't available at the time and titanium was only just coming on board. And there was a huge amount of lessons learned, and we still did a number of things wrong. So for example, the array of 9 OMT components, this RF component, were all aligned at 90 degrees to the bed, and they're all well, you just wouldn't do things like that nowadays. So we learned a lot during that program, and we saw a cost reduction from 15,000 down to approximately £1,000 per part. So we didn't fly it at the time. It was an R&D project. But moving on to the next slide, our first additive part that flew was the part in the photo on the top left. It's sort of a tripod connector for, you can see the assembly in the top picture. So we have what's called a biaxial sun sensor and telemetry support bracket, and that little part was the first additive part that went up on the Atlantic Bird 7 mission. I think it's got a different name now. Eutelsat renamed their fleet, and it was launched over 10 years ago. So and the picture on the right, it's a nice picture of a rocket. We all like rockets. So first flight 11 years ago. Moving on. So many of you will be familiar with this assembly. It's called the TMTC bracket. It was the first topology optimized design. It was, let's say, very, very difficult to design. We used CATIA and FEMAP. You wouldn't use these tools 7, 8 years ago. That was all we had to design. We've got some wonderful software tools now to create this complex geometry. So that was funded by the UK Space Agency, and the credit to my colleague who did the work on the screen. That was manufactured from aluminium silicon 10. We wanted to produce the part from Skelmalloy, but many of you will be familiar with the Skelmalloy journey, and the first batch of Skelmalloy was highly spheroidized, and the next couple of batches were sort of, we always described them as potato shaped. So the Skelmalloy wasn't commercially available at the time, so the fallback position was aluminium silicon 10. And just to note, we actually performed a T6 heat treatment, and I'll talk about that heat treatment soon. So if we move on, just worth mentioning that one of those flies on every satellite since, I guess, the last 6 or 7 years. So Materials that are now qualified for within Airbus defence and space, we've got titanium, 6Al4V. Titanium additive products form perhaps less than 5% of the total additive parts that we've got flying. Aluminium silicon 10 is most commonly used, and in 2018 we went round a bit of a tour of Europe to find who had Scalmalloy to do our qualification with, and we had a bit of an open competition, and we selected a Belgian company called AnyShape to do that qualification. That took place in 2019, and this Scalmalloy, as you're probably familiar with, is a high strength alloy allowing lightweight design. So the chart on the bottom shows the red bars represent in order left to right the 1000, 2, 3, 4, 5, 6 and 7000 series aluminiums. The axis on the left is yield strength, so we can see a good old 70-75 is around about 500 megapascal yield strength. Problem with that material is the corrosion properties are not great. I think it's due to the reduced chromium content. So I mentioned about T6 aluminium silicon 10. We qualified the T6 heat treatment on the TMTC bracket, and this gives you a yield strength around about 260 megapascals. And we kind of got away with it with the geometry of the TMTC bracket because there was lots of nice triangles supporting many of the beams. We then tried to heat treat other components that are a bit more spindly and less well supported, although they're fit for purpose in terms of the design and the stresses. And we had some significant distortion, so we went around a few loops of trying to correct that. And we basically, our fallback position is we do not heat treat a T6 condition aluminium silicon 10. We use it in the stress relief condition. And when you look at the yield strength of the stress relief condition, it's about as poor as a pure aluminium 1000 series, so really low strength. Now, one of the winning themes of Scalmalloy is to get your high strength, it requires a stress relief, which is 325 degrees C for 4 hours in an air cool. Thus, you're not introducing this quenching, and you get yield strength of over 450 design allowable. So in the qualification, everything was near the 500 mark. And then there's a knockdown factor for scatter between batches. We've declared 450 megapascals. So that now enables you to really lightweight designs compared to an aluminium silicon 10 in a stress relief condition. Next slide. So Scalmalloy, where are we now? So qualification took place in 2019 via AnyShape. We saw an absolutely superb surface finish. So typically 5 microns, so very, very good indeed. The chart on the left, the blue bars represent the yield strength. And what's quite interesting is the recycle or the batch of parts we made with the lowest yield strength were actually virgin Scalmalloy, which was interesting. We never quite worked that out. But obviously you can see here that there's no real drop off, or I would say no drop off at all. There's a small fluctuation. And I think coming back to Nick's great presentation earlier, talking about powder handling, there's some ways that you can, some IP we've achieved over the years and fed back to AnyShape about good powder handling and robust powder handling to make sure you will get a drop off eventually, but the longer you can keep the powder good to go. And also the elongations, you can see the triangles, everything's sort of between 12 and 14% elongation. So some really good material properties and very, very repeatable. And this is what the type of data we can present to our customer to show that we've got a highly repeatable process. So in terms of, I mentioned the surface finish, we've got excellent geometrical accuracy when we 3D scan them. I can't remember the numbers, but it was about 98.5% of all the geometry was in plus or minus 0.2 of a mil. And so anyway, I can't remember the exact numbers, but hugely geometrically accurate, which for RF parts is very, very important, not so much for mechanical brackets. And just worth noting that the bulk of our components that we do fly are RF components for the payload and the antenna systems. A couple of months ago, I took delivery of 120 parts for Neosat. So from Neosat number 3 onwards, we're seeing a good number of Scalmalloy parts being introduced. We're looking to introduce more. And we're also developing a robot for in-space manufacturing that was kind of hinted on earlier. That's development's been in the lab for a number of years now, and I think we've just took delivery of, I think, 39 parts for that robot for the TRL-6 robotic arm assembly that we're building. If we can move on, please. So this is one of the slides I swapped out to a slightly better cost model. So let's look at the cost for an aluminium silicon 10 versus a scalmalloy design. So the way I present this, if we look at the TMTC bracket that I presented earlier, that was aluminium silicon 10, when we had a machine in Stevenage, we were depositing around about 20 grams of material per hour. So the machines, we all know they're expensive, and if we attribute an hourly rate of around about 100 euros an hour to run that machine, we could all argue whether that's correct, whether it should be 90, 80, 120, but to keep the maths simple. So if we look at a TMTC bracket in aluminium silicon 10, the cost of the powder without any factor for wastage is really very low. Typically, when we used to buy aluminium silicon 10, it was around about £55 a kilogram. So half a kilogram of bracket, a bit of wastage, it's probably, 30 to 40 pounds per bracket. Now, if you're going to deposit half a kilogram of material at 20 grams an hour, you're looking at around about a 25-hour processing time. You could argue that you've got a setup time and time to allow the machine to cool down would add further cost. So that's £2,500 of processing time, some machining, some scanning, some quality time attributed to the paperwork and the validation of the part. Now, if you're going to redesign that part using scalmalloy, what we've typically seen is you save between 30 and 50% mass. So if we now say the redesigned scalmalloy part is going to be 0.3 of a kilogram for the same load cases, and we've done quite a few studies comparing the two materials, as I said, between 30 and 50% savings. So if we save around about 40% to go middle value. Now, scalmalloy typically is around about 200 euros per kilogram, so nearly 4 times the cost, but we're now only using 0.3 of a kilogram of it compared to 0.5. Yes, there will be a bit of wastage as well. But the key thing is that the AM processing time, because we're only now got to deposit 300 grams, is that you've got the time attributed to the machine cost is £1,500. So for investing in a more expensive material, and if you lightweight your designs, you can't just build the same geometry, you've got to lightweight it. You can, your big cost saving is attributed to the time on the machine, then all the other costs will be the same. So one of the key messages here, there is a thought that scalmalloy is an expensive material. Yes, it is. But if you use those, the yield strength, nearly 3 times that of aluminium silicon 10 in the stress relief condition, you use it and you load the component up well, you stress it to a good limit, then you can lightweight and save money at the same time using scalmalloy. So if we move to the next slide. So I've been fortunate enough to be able to show the part on the right. This is development from 2 or 3 years ago, but the highly integrated antenna feeds of the pictures on the left are a mission called Sky Brazil that we did in 2016. I think we delivered it. So you can see there's hundreds of piece parts there. Also, if you look at the picture on the top left, you'll notice that all the antenna feed horns are mounted to a large plate. Hold that thought and we'll bring that next on to the topic of WAM. But you can see there's hundreds of piece parts, you've got lots of individual drawings, you've got bills of materials, you've got work instructions, manufacturing history records, thousands of hours to assemble it. And these are now being replaced with multi-antenna monolithic single parts. So you've got waveguides, you've got other filters included within the feed horn. Mechanically, they're all joined together. And these prints are being done, well, they're being built for flight now. So that was an early development. So you can see that even if you're looking at the waveguide ports, the waveguides have a pitched roof geometry, so they're self-supporting. So the antenna group, we've really got to know AM very well over the last 15 years, and we are really effectively designing for it very well. And these designs now have the envelope of 398mm by 398 to give a 1mm border all around for an EOS 400 machine. And then effectively what we do, we take 4 of these monolithic prints and we strap them all together for this active antenna assembly that we're doing. So it's really, I always call it the gold standard of AM within Airbus, where literally thousands of piece parts then just go to single prints. moving on. So let's change focus onto wire arc. I don't think I'm going to be directly repeating anything, but some of the messages will be the same from the presentations of Ian and Richard earlier. So we've been following the Cranfield University process for nearly 10 years now. And what it can do, it can produce an inlet shape without tooling to replace forgings. We know that, it's been mentioned. And what we see is that low volume space products can be dominated by tooling costs. Forging lead times can drive a schedule. And sometimes that schedule can mean you've got a reduced amount of time to design your component. And sometimes you might sort of over design it because you're forced to get your design out there to commit the forging. And therefore you're potentially adding cost and mass because you've not got an optimized design. Process scalability, not a factor. We've seen some huge parts. I think Cranfield University built some 12 or 13 meter demonstrator part. Now, the high deposition rates, nobody's put any numbers on the table yet, but I've mentioned the 20 grams per hour for powder. Typically, we're seeing 6 to 8 in titanium. But the other thing is that nobody's mentioned is significantly cheaper raw material compared to powder. I would always say that a wire is typically half the cost of a powder, which is another benefit. And another great thing now that the process is now commercialized, you've got the DfAM offering, you've got the guys in Glen Ormond, you've got the Meltio, you've got WAM 3D. So you're now seeing from what was lab mode in Cranfield a number of years ago and elsewhere, we now got turnkey machines that can be bought by industry, which is great to see. So if we move on to the next chart. So this is a picture of a propulsion tank part that I think was manufactured in 2015-16. Somebody talked about the inert environment it's in. In this case, you might just be able to see a see-through plastic tent covering the entire robot. Fairly inefficient in terms of argon usage, but this is how Cranfield did it 7 or 8 years ago. So this tank I'll talk about a bit more if we move on to the next slide. So I said, hold that thought about the antenna panels. So I first approached Professor Williams and Gilo and Philo 2013 to talk about making these blanks that hold the antenna. These blanks were made from titanium. The reason they were made from titanium was to keep the antenna stability. So if you've got a geostationary satellite 36,000 kilometers from Earth and the panel starts bending and all of a sudden the beam pattern on the Earth might be moving by the order of kilometers, these parts were made from titanium because the CTA is much lower than aluminium. So these panels were typically about £50,000 each. We'd buy a £10,000 billet and then we'd spend hours machining it. So the machining rates of titanium are extremely slow. And I talked to Professor Williams about making titanium blanks. At that time, there was no funding to look at that. But what we did in 2014, we used some of our own R&D money to commission these 2 hemispheres that were meant to be a propulsion tank early proof of concept demonstrator. So we built 2, or Cranfield did. We machined one back, and you can see the targets on the left-hand one we did with the 3D scanning. And that project was successful enough that in 2015 to 2017, we ran a project with Innovate UK. I'll talk a bit more about that. I'll also talk about the images on the top in the middle about a high-performance antenna tower. Obviously, the RoboWAM system now is commercialized. I mentioned about the systems being commercialized, which is great. I was part of the RoboWAM project, working with a consortium to help take the technology from Cranfield University in lab mode to make it into commercially available machines. You've seen the test walls on the top right from Richard's presentation. They're mine. We've also had a part made from Meltio. And in 2023, those walls would have been fully tested and the WAM titanium 6.4 will be ready for flight. Incidentally, the 2 products that we've built from WAM have also achieved TRL6 status. So if we move on. So this was sponsored by Innovate UK, working with Cranfield University, the Nuclear AMRC in Sheffield did the machining. So what we did, the goal of the project was to design, manufacture and test a representative spacecraft propulsion tank. So we did a conceptual design with all the key features you'd see in a real propulsion tank. So internal features, external features, and thick walls graduating to thin walls. Manufacturing obviously done by Cranfield University. If you look at the picture on the bottom left, we talked about a substrate plate. Could it be part of the final product? Well, that's quite a key point, because what we did on this project, we actually used a round bar, and this actually gives you an advantage that you can now use this to help datum your 3D scan, because what you can do, you can overlay the as designed against the as built in CAD to work out if you put enough meat on the bone that you get a full cleanup. So that helps you datum it for the CAD inspection, and also the alignment on the machine as well. So really quite an important point. Nuclear MSc did a great job on machining. The Welding Institute welded the two tanks together. So we built two lower shells, two upper shells. We cut a quarter section out of one of them, and then we did a test on the part on the right. This was the only time in my 20 years in Airbus I've been allowed to blow anything up. So the test predictions on this one, it would fail between 1,400 and 1,500 psi. So we did a number of pressure cycles before the final burst testing, and this failed at 1,491 psi, so very successful. Some of the doubters said you built it in layers, it will delaminate in those same layers. So the actual failure mode, I hope you can see my cursor. So at this junction here was the area of the highest microstrain. We've still got the strain gauges attached on the other side. And then the crack propagated upwards until the cross section got slightly thicker at the upper mount, and then took the path of least resistance. And at the same time, the crack grew downwards until it hit this external flange, and then the flapper material sort of came away here and here. So that was the failure mode. So the point being, very successful test and in line with the test predictions. If we can move on, please. Sorry, just taking a drink there. So these are the test predictions. So we predicted that it would yield between 1250 and 1350. And I mentioned the predictions earlier. I'd forgotten, I'd chucked this slide in earlier. You can see the strain gauges. So we constantly measured the microstrain throughout the testing. Nothing more to say than it was wonderful to be part of a successful test campaign where everything lined up with test predictions. So the testing was actually done in a brand new pressure test facility at the Welding Institute in Cambridge. We're actually the first customer to use it. Okay, if we can move on. Yeah, so I obviously did the presentation earlier today and I've forgotten the exact route. So I did mention this earlier. So crack initiation point where the circle is, the yellow lines where the crack went up and down, the blue arrow taking the path of least resistance, and then the two green arrows where the flapper material starts to come away. So it looks a fairly catastrophic test, but what actually happened, it shows you that the entire vessel was under a very uniform strain, which is what you want with your AM designs. So if we move on, we'll talk about the next significant product we've designed. So I've had to sort of grey out the flight hardware because of IP, but this is a real mission, and unfortunately we saw the opportunity too late. I worked in the antenna group for 12 years and I was back in that group, perhaps chatting to some ex-colleagues, and I saw this on the screen. And just to give you an idea of the technology, this lower octagonal tapered cone was from carbon fiber. There's some honeycomb panel technology. The two antenna feeds are supported by machine brackets. There's actually an additive bracket on the top, which is nice to see. This was my original PowerPoint sketch. So I had an idea that we can make some, dare I say, traffic cone type shape that was latticed out. And then we can support the upper antenna on the top of the cone. And then the other two antennas were not supported by the honeycomb panel, but somehow we designed some 3D printed brackets to support to the side of the cone. Top right, you can see the overlay between the two. And then I got one of my graduates to redesign the additive brackets to support the antennas. And we did some finite element analysis work. And this sort of moved on from a concept to let's do some finite element work to let's build a aluminium version, which was done by Glenn Allman Technologies. And that's the part you can see in the bottom left. And then I wanted to take it a step further. So if we can move on to the next slide, please. So I then got some funding to build a titanium part, and the idea was to do a full vibration test to validate the design to get a TRL 6 status for this type of structure. So we ended up designing some mass dummies, and again, the part was made by Glenn Technologies, did a fantastic job on the deposition and machining. The whole thing was kind of designed in other words, for manufacturers. So I shouldn't trivialize this because the guys did a brilliant job, but you turn the OD, turn the ID, a bit of tooling to support it during the manufacturing process, and then simply mill the pockets out. I sort of slightly over trivialized it, but yeah, fantastic job on that. And then a couple of years ago, we did the full vibration test, and it was a rather benign test. Nothing went wrong. It passed the test, and we got TRL 6 status. More importantly, the figures of merit. I can't show the real numbers. I've had to disguise them by pound signs. It's over 50% saving for the non-recurring. So when you're designing one-off antennas, rather than designing this multi-part structure, the design phase is a lot quicker. So you're just making a CAD model of one part, you're making a thermal model of one part, you're making a stress model of one part, rather than this difficult complex structure. When we do finite element analysis of structures, we end up looking at the loads in every single bolted joint to make sure every single joint is robust. You've got less joints here, you've got less analysis time. The recurring costs, again, under 50% of the recurring costs that we saw on the satellite. The mass, I've put two different mass values. One is aluminium, the second one is titanium. The choice of materials will depend on thermoelastic distortions, again, antenna pointing. But the worst scenario, you've got a titanium tower to minimize any D point. You've got 50% mass saving. Your lead time saving is again very, very good. It's probably, the existing design was probably nearer 40 weeks. So the figures of merit is ticking every box. And we've seen that with both these applications we've looked at, and that's what's driven us to complete the formal material qualification. So if we can move on, please, Rob. So moving on to the next iteration, if you like. So I don't know if you know a company called AI Build. Luke Rogers, former 3T. I've been speaking to him over the last year or two. They've got their robotic system with the Meltio engine on. And Luke asked me for applications effectively to test drive their setup. And they've produced this part. It's a representative part from the antenna tower. And what the idea now, rather than building a full traffic cone and then machining it down, the idea is that we can now start producing complex, very near net shaped blanks to be machined. So saving on raw material costs, saving on deposition time, saving on machining time to get it to a nearer net shape. So this is an exciting piece of work being done by the guys in London. Can move on. So I thought I'd mention our own Print 3D portal. The idea of this, it's an internally developed portal. And what it does, it digitally connects every Airbus employee with every Airbus 3D printer to, I'll put in brackets, almost every 3D printed part. So really simple to use. You can just zoom around the map. You can zoom into all the different sites. This is slightly out of date. We've got printers in the UK, in Broughton, Portsmouth, and Stevenage and Filton. So all the printers have been uploaded to the database. The good thing here is that if you want to, for example, find out in Airbus if where there's a Mark Forge printer, you can do the search for Mark Forge and it'll tell you there's a few printers in Germany. It will then direct you to the person who is linked to that printer. So you can therefore go and talk to the person, say, can I have a demo print? So the idea being that we're sharing all our resources. If I want to get a part made in Filton, I can speak to a local machine owner, he can do it for me. So if we move on to the next slide. So we've also done linked all our FDM printers, and to request a part, it's fairly simple. You can see the graphic there. You can select the file, you can put the quantity in, description, tell them the shipping address or collect it, and put a few other bits in. Submit your request, and if you want a FDM part, it's done for free. And we recognise that within a big company like Airbus, if there's a £30 part being built, we'll probably end up spending £50 transferring that £30 from Department A to Department B. So the idea being that it's centrally funded. It means that all the Airbus employees can get their hands on FDM prints effectively for free. Obviously, we've put the metal printers on, but there is a charge for using those. And it's a great way of promoting the Print 3D. And in a way, I've been talking to the guys here to see whether this can be made into a more industrial platform where we can see where all the printers, for example, in the UK are. So we've done that within Airbus. Why couldn't there be a similar portal so that if we want to find out where there's an SLM 500 in the country, we can do that, and we can find out where that is, and we can connect to the company that owns that machine, because we can't keep up with our knowledge of understanding where every machine is in every company in every location. So I'm talking to the guys who developed this portal about potentially industrializing it. I think that might be my last slide. If you just move on. I know I added something about universities because you put something in the title. So just a mention of the universities we're currently working with. We have year-on-year final year undergraduate projects with the local Hertfordshire University down the road. We have the same with Imperial, and we've got a current Airbus employee. He was actually a final year student doing his project for me a number of years ago. So it's a nice carrot for these young engineers. If they do a project with Airbus, potentially they can be fast-tracked for the graduate recruitment scheme. We've had ongoing projects with Southampton University in their CT scanning department, and previous support to a PhD at Cardiff. And then just the final words about academia and industry. It's I mentioned to Dave Wimpenny at the MTC that I'd like to see an event where industry meets academia, so that we can't go. We haven't got the time to go. Sorry, my phone's going. Hold on. Okay, so I haven't got time to go around all the universities and find out what they're doing. If I went to a university, I may go to one department, and they might have other departments with other interesting projects. So it'd be great if there could be some event, and maybe Rob, you can perhaps coordinate some event. And the idea being that academia goes off at sometimes a tangent, and they need reining in, and we could potentially meet them and help them to tune their products or their projects to product needs. So for example, if they're developing some additively manufactured antenna, but they're doing a different frequency range to the one we'd like, we could say, well, maybe we can help you and we can tune it to something that would be more suitable for our needs in the future. And I think academia needs to understand and what the industry needs are. And during these such events, we can also propose new projects to academia to find out if they want to work with us, and also general networking. So I think I'd like to see more of that, because there's some great stuff being done at universities. Some stuff perhaps is usable but would need tuning, and just to perhaps link in and understand what equipment and facilities are at all these different universities could be of use to us. There's nothing stopping us working with universities on, for example, European Space Agency projects or UK Space Agency projects. So I think, I'm pretty sure that is the last slide now. If you go to the next one, it's just got the questions and a collage of some of the photos of the parts we've done over the years.
Well, thank you very much, Jason. We will, I'm sure, have some questions. I think I don't want to put too many words in your mouth, but I think we've discussed before that you was quite open to sharing, or there was some potential CAD and some qualification kind of requirements that you was quite happy to share. I think listening to the points you just made about industry to academia, that would be a really good way to start that process, is about providing industry standard geometry, industry standard methods, and then letting academia come back with data. Because you're dead right, and I'm happy to try and facilitate some of those areas of that you just raised. And I think Richard, Ian, correct me if I'm wrong, I think you'd be quite happy to see that on the part side, and Nick equally in terms of parts to powder. So I think there's definitely a need, but you're right. Industry needs to start giving academia something more relevant. Otherwise, it's always the GE jet engine bracket on GrabCAD, which the students seem to jump on. So if you've got things like that, that'd be great to try and open that as a start of sharing.
Yeah, so what I have done in the past, I've given out the Airbus qualification test plan for WAM and powder to suppliers. The reason being that companies like Glennorman, Stroke, Forge 3D, if they could, under their own cost, whether they can get that funded or part funded, if they could then do all the qualification testing, and the company owns the qualification test data, if a company approaches them, they can say, well, we've already got all this test data that's aligned, okay, it's aligned to Airbus. But that would mean that smaller companies would have to spend a lot less money on qualifying if they can accept some of the qualification data done by, for example, Glennorman in their own test campaign. There might be a few additional tests required, but it could help people qualify well, either powder or metal a lot cheaper if the manufacturing companies hold the test data. And this is an approach we took with Layerwise many years ago. We looked at all their qualification data, we effectively audited it, and we said, okay, it's good data. We wrote a qualification test report based on their data, and that meant that we didn't have to do a huge amount to get them on board. The big Airbuses of the world can afford to qualify material, but certain smaller companies can't, and that might be a showstopper for wanting or for being able to use this technology. You know, it might cost £100,000 to qualify.
Yeah, and I guess the question back is the expectation always going to be UCAS accredited labs, etc., etc., or is data in terms of that initial conversation for you?
So in terms of actually physically testing the part, it would need to be a NADCAP approved supplier, certainly for Airbus. But that's something that we advised Glennorman on when I gave them the test plan. So I said, if you want to go on your own and build your own parts and test them, I would like to see NADCAP approved test house, not just somebody down the road. So that was actually in the test plan I provided, that requirement.
Yeah, okay. Good. I wonder how NADCAP approved university labs. I wonder if that's something to explore. The universities I've been in have got quite unbelievable test capability. Could they go down the route of approval? Maybe. We have some questions. So Scarmalloy. So the question: Scarmalloy WAM certificate, WAM titanium material certified for airworthiness on rotary aircrafts. So I presume it's an open question. Do you know if Scarmalloy and WAM titanium is certified on rotary aircraft?
So the guys in commercial aircraft in Filton are doing their own qualification of both Scarmalloy powder and WAM titanium for aircraft. So within the space industry, the reason we can claim that we've been flying additive parts for longer is because we're unmanned. We don't have the authorities to answer to. We don't have the fatigue requirements. So we tend to get parts flying a lot quicker than aircraft. So those two materials are being qualified currently by the guys in Filton for aircraft applications.
And I think Airbus helicopters have been pretty active in France. I'm not sure where they're at with WAM. I don't know if you know in terms of purely on rotary craft. I don't know if you know anything about Airbus helicopters AM plans.
So there's a lot of WAM work being done in France using a Sayaki machine. There's some work being done in Filton on WAM technology where Airbus have built their own system. That decision was made before the system started coming to market. So for me, it's great that the commercial systems like the Gilmore and the Meltios are available. Glennorman Technology are an approved supplier for flight hardware for Airbus Defence and Space. And obviously, we need to understand how the transition between Glennorman Technologies and Forge 3D is going to happen. So I need to talk to Richard and his brother Jamie in the new year about that, because we'll effectively be working with a startup, which becomes interesting in terms of financial history and other things, but something we can work on. And we just need to make sure that the technology developed at Glenormand is smoothly transitioned to Forge 3D.
Good. No pressure, Richard. Next question. You must have made a comment, Jason, about Scamalloy properties dropping off. So the question is, what do you mean about the Scamalloy properties dropping off? Do you run out of reusable powder before the drop off, or do you have to add more powder as it's used and see a drop off after a number of uses?
Okay, so we did the usual virgin powder plus 10 recycles. The chart earlier, I said there was no drop off, but everybody has finite budgets, and that's what we had. We had budgets to do 10 recycles. My understanding is any shape of processing parts up to 30 recycles, but again, it comes down to powder management. And Nick gave a very good presentation on it. I can't stress enough that, you know, powder management from day one to its final days, it's got to be well looked after. And so I can't answer the question. We know that after 30 recycles, everything still remains as good as you know, numbers 1 to 10.
And I think from the reality is different. You know, we talked a lot about powder when we're talking about parts, but the machines themselves do have an impact here. Not all machines are as clean as others, despite what they might claim. I think, you know, Ian, if he's still here, he used to work at Renishaw, and I think Renishaw took great pride on the gas flow aspect of their system, and Scamalloy needs a really good gas flow system. In particular, Scamalloy is one of the problem areas, if you like. So some machines will also give you different problems, and that cliff edge, if you like, is certain materials are more sensitive to oxygen than others. So Scamalloy, generally speaking, can be quite sensitive to oxygen, but if you don't have the oxygen in there, then, like you say, 10 builds is fine, but maybe you would get to 50 or more builds. It's all about controlling that oxygen content, isn't it? And machine does have a factor in that. It's one of the things that we don't have is a directory of all of the different experiences people have monitoring powder consistently, because you're in the business of making parts to build satellites and support the launch efforts. You're not in the business of constantly experimenting with powder reuse. Good. Any more questions? Anyone in the room away from the chat wants to shout out, or are we